Okay. Whilst we get started, is it running?
Yeah.
I just want to thank the organisers for inviting me. I've had a fantastic time both at the scientific sessions and at this outreach session so far. I'm from Cambridge, as you've probably gathered. What I want to talk about is, in particular, something which we call the Senior Physics Challenge, and I'll give a brief overview as to what our aims and objectives are. In the first instance, I want to just thank the other speakers in this session, because I think it shows exactly what ICAM is very good for, i.e. connecting different people who do different things at different levels. Okay, so we have one level where we have online museum, we have other things such as the emergent labs. This is another example of what we do very well, which is to engage people on many different levels with many different objectives. So we do the same in Cambridge. What I have to say is, in order to be successful in our goals, in order to survive into the next century, as Martin Rees, my master says, we have to change various things. Okay, one of those things is we have to change how we view the world. Okay, how we view energy, how we view our lives, medically, scientifically. So one level we engage with the population. As scientists, we have to engage with government, we have to engage them with energy policy, we have to engage them on medical policy, having informed decisions. Medical meaning things such as science as opposed to pseudoscience. For example, homeopathy in the UK accounts for something like 50% of sales in chemists now, okay, and that's a scary number. I didn't believe it myself. So there's another level of engagement, which is equipping voters to vote in an informed way. Okay, so one thing to decide is, in the UK, is to decide whether we want to build the next generation of nuclear power stations. So unless we can engage the voters in making an active choice whether to build or not build nuclear power stations, we won't be successful in what we want to do, which is survive into the next century, I guess. Okay, and another thing about education is we want people to embrace science and technology rather than fear it. And there is, even though we are at this stage very well technologically developed, everyone here carries a mobile phone, there are lots of people who still don't want to understand how mobile phones work. They don't want to understand how science works. And that's something I would hope that we, as part of ICAM, will want to counter. Anyway, in particular, what Cambridge does and what I want to do is we want to produce and encourage the next generation of scientists. So, this is an overview of what we do in Cambridge approximately. So we have a Cavendish Museum which builds on the history of Cambridge, such as the discovery of the electron, such as the discovery of the neutron. So the Cavendish Museum is something which is open to all. We also have teacher fellowships and teacher training enterprises. One thing about the UK is that A-level, i.e. 17 to 18-year-old teaching, is typically done by physics graduates. Okay, if we just look at physicists, only 1/3 of UK 17 and 18-year-olds are taught by physics specialists, people who have a physics degree. And so we try and support that by training people who don't have a first degree in physics in some of the areas which we think is important if they want to teach physics successfully. Okay, in addition, we have various other school workshops and master classes. We have something which is called Physics at Work, which I'll talk briefly about, the Senior Physics Challenge, which I'll talk in depth about, and something else called Physics Olympiad. Okay, so Physics at Work. Our education system typically has a very high degree of scoping and speciality. So typically one does about 10 subjects when they are around 14 to 16. So this is the level where you take a school leaving certificate in inverted commas. And at that point you are deciding, around 16, deciding what you want to do with your life. So after 16 you typically will choose 3 subjects to go into, and those subjects are typically just your subjects at university. So if you're a physics major or science major, typically at 17 and 18 you will choose math, further math, physics and maybe chemistry. Okay? So very much more specialised compared to the US, where you don't choose your major until possibly your second year of uni. Okay, so there is a tremendous importance in trying to stimulate and encourage people who are 14 to 16 to make choices in their A-level studies in science. And part of what we want to do with Physics at Work is to showcase everyday science and its involvement and excitement. Involve them in its excitement. Okay, so what we do is we bring about 700 kids in of that age group, and we give them demonstrations by active researchers. Okay, people who are doing active research, be it in condensed matter, superconductivity, be it in industry. So we have people like Ford, Rolls-Royce, Kodak telling us about different aspects of their work. So this is run over 3 days, typically, and once a year, with 700 local students who come in. They come in, they see a short presentation by the respective presenter. There might be a practical demonstration, there's a hands-on element, and there's also an element where kids can ask questions. We also put a booklet together which explains some of the ideas at greater depth, and kids do like the idea of having a booklet to take away and explore. There was a video of this, but this isn't my computer, so I don't have that actually. I'm sorry. Okay, so in particular, what do we want to do regarding the Senior Physics Challenge? Well, what we are very good at is having very specialised people teach our university courses. And we know we can do that level of teaching to encourage people who are at the upper end and are prospective scientists. We know that we are also part of an organisation called the Institute of Physics, which does very good outreach for the general population, producing material which is suitable for the general population, educating people who want to basically make informed vote decisions, okay, reading the Sunday papers and being able to make informed decisions. So what we want to do in Cambridge is, in particular, motivate those people who want to do science. Okay? And something we've noticed recently is that, strangely enough, the most able school students, okay, who have an aptitude, i.e. they are mathematically inclined and they have the aptitude to do science, are not actually opting to do physics. Okay? And instead they're doing things such as medicine, some do mathematics, and part of that is because there is a huge misconception about what physics and natural sciences is about in general. And that stems primarily, we believe, from the removal of mathematics and hard problem solving from the school curriculum. So, and this is in direct contrast with what the university wants. The universities, okay, so if you want to match up how our university system matches up with the US system, typically you were to choose your major a year into or 2 years into your university skill, your university schooling. Well, we choose that sort of effectively 2 years ahead. You choose that, you make that choice as to what your major is 2 years ahead, typically when you're sort of 18. And what we require when we make that selection is that we demand mathematical fluency. Okay? And that isn't given prominence in schools. Okay? And what typically happens is that students are increasingly surprised and disadvantaged by the discrepancy of this expectation that universities have and its reality. A typical figure you put on the attrition rate for physics courses is about 60%. So 60% of people who come in to a UK university to do physics end up not graduating with a physics degree. Okay? And that's a tremendously high number. Okay? It's just unbelievable that 60% choose not to go into physics. They may move into a different science or they may move into something else, but 60% do not graduate having chosen their major to be physics. And so part of what we want to do is just show that doing physics is not the same as physics appreciation. There is huge numbers of popular science books, especially in particle physics, where they explain string theory and how exciting string theory is. But being able to read those books, being able to see programs about science and about physics in particular, is not the same as actually doing physics. And so what we want to do in our program is to basically, one, demystify what physics actually is, make it accessible to a wide range of students transitioning from A-level to university, And in particular, because we are Cambridge and there's a huge history behind us, we can use that history and that name to encourage students to come with the intention that eventually we will broaden out and franchise out some of our programs to other universities, okay, using the Cambridge brand. So, 5 years ago, we introduced a summer school held in Cambridge, and you probably can't see it here, but this actually is the Maxwell Lecture Theatre in Cambridge, where James Clerk Maxwell himself lectured. So it's special. We get a group of kids, and they've read something about the history of Cambridge, and to be able to sit down in the same seats that people once heard James Clerk Maxwell, Rayleigh, other great men lecture is just a fantastic experience. Okay? And typically we have the money and the room for about 60 students, and we can only run this once a year because of financial constraints. So we have 60, and we're oversubscribed typically by a factor of 5. Okay, so what we give them is basically, we fill in the gaps of what they might need to know. They get a preview course as to what physics is about. So they receive intensive tuition on basically problem solving. And I'll give you some examples of what we mean by problem solving and some experimental skills. Okay. The other thing about the UK education system is that because of health and safety constraints, basically, to lead in order, no experiments are done by students in school. Okay, so we show them what it is to do an experiment, okay, what it is to measure G, for example, a simple measurement such as what G is. With a pendulum or a road and ball experiment, they can't do in school. So anyway, we try and fill in some of those gaps. So we spend about half the time on problem solving. We spend sort of the afternoon sessions on general physics, things to bring them up to date. We have lectures on ice formation, okay, and ice formation regarding and the contrast between the losing of ice and global warming. So that's done by an expert. We have David Mackay, who's a lecturer in Cambridge, and therefore he often comes in and does some work on that area. So current research topics we also put in and give them a flavour as to what physics is about. We give them entertainment sessions. We give them Fermi-style problems, and I'll give you some examples of that. And we give them missions talks and the like. Okay, so what I mean by Fermi-style problems is this. So here's a series of questions that Fermi might have asked. So what we've determined is basically, one, these activities give you scope to realise that actually with very, very little knowledge, but a degree of ingenuity, which all these students have, they can work out how many babies are born worldwide per year. Okay, how many diapers are needed, for example. We typically put them into groups of 5 or 6, okay, and everyone comes with individual knowledge. Okay, so some people might know how many people there are in the world. Some people might know the population of the UK, for example, and be able to scale that up. Okay. So what we realise is students come from a very, very wide background, and students know a lot about various things. Okay, and together they can talk to each other and be able to do certain things. Okay, the fact about physics is we don't know everything. Okay, we know isolated pockets. We have experimental data, and they show us different facets of what reality is. And we try to put together and solve what the problem is. Okay, and this is what Fermi sort of asked. Okay, effectively, how many piano tuners are there in Chicago? And okay, with very small assumptions, very small number of assumptions, we can move very far and actually make a very good order of magnitude guess as to how many physicists or piano tuners there are. Okay? And what we give students is we give them the idea that actually, as a physicist, these are the type of problems that they have to think about. And if you were to solve a real problem, one of the first stages is to work out approximately what order of magnitude certain things are. And then once you then go back and actually solve the problem in great detail, you can compare and you can realise, oh, one of them disagrees. If they disagree, either your order of magnitude was wrong, in which case you learned something, or alternatively your analytical answer was wrong, in which case, well, you can fix it up. Okay? And these are skills that 20 years ago students would have developed prior to coming to university. And what we find is actually students are initially very much afraid. Okay, any of these questions, you just look at them and say, well, I can't do it, I don't know the answer, it's not part of my schooling. Okay? But when you get them together in a group of people, in a small group, they can actually go very, very far. Okay? And one of the advantages of bringing lots of people together is that they can cross-fertilize each other. Everyone has a slightly different background, and they can produce something which is greater than the sum. Okay? And that's something we see time and time again. When you have groups of people together in the same place, you have ideas which come about, which don't come about otherwise. Okay? Mechanics example. So let's give you an example of what we do during some of our sessions. So a typical session is we have a sort of half-hour intro lecture. So a mechanics lecture might start basically by discussing Newton's laws. And everyone will have met what Newton's laws are, and we give them very simple examples initially. And they work together, both with themselves, and also we have teachers circulating around. So typically what happens is these kids, 60 kids, are in the lecture theatre, sitting in alternate rows, and they start problem solving together in their own age group, and then we circulate around and we try and help them. So, problems such as this. We've got a trolley of a certain mass. You give it a certain force, it accelerates. We ask the question, if these masses, which are also on wheels, aren't accelerating with respect to the big trolley, what force must we apply? Okay? And these problems are typically not problems they've seen, even though they've met F equals ma. To apply to slightly more complicated scenarios, they won't be familiar with. Okay? And we give them the confidence to do this. Okay? Here's another example. What we find is that students are surprised by these questions, but then they realize the power, something very simple, Newton's laws, 3 laws, and you can basically describe pressure of a gas. Okay, so we later show them things such as kinetic theory, just deriving in a very loose sense why PV equals RT. Okay, and we find that they really do enjoy the deep understanding and the new skills they acquire. The other thing is, of course, this isn't a standalone exercise. It gives them a platform for self-exploration. Okay, we typically write back to the schools, and we only take 1 or 2. Well, we typically take 1, at most 2 students per school. So every year we give some information back to about 60 schools, and we try and take different schools every year. So we've been running for 5 years, 60 schools times 5 years. So we're getting up to 300 odd schools, various bits of information on how you might begin to approach science as physicists at university might approach it, and what we might want. Just some final remarks. What we have evidence of is that kids are applying to do physics and also in Cambridge, which is a side effect which we quite like. We find that basically 80% of students say that they were helped in their university application choice by this week. Over half say basically their enthusiasm to study physics had increased. Okay, so that's very pleasing. Students enjoy the hard problem solving. And one thing we find is actually we ask people why they chose medicine. Okay, medicine is a very hard course, and the fact that it's hard doesn't put them off. The fact that it's hard to do mathematics hasn't put people off doing mathematics. And it's basically that, at least in the UK, there's no realization what physics actually is at university level, and what science is on a more general thing. Okay, so the same remarks can be made about natural sciences in general, as opposed to just physics. But being a physicist, we're focused on physics. And the most important thing that I find is that people aren't alone. People realize that for the first time that their interest in science, they're not alone. They're not at home looking at a website or watching a TV program or reading, but actually there are other people who are interested in the same sort of things, and they get to sit with 60 other students who are as talented, as interested, and this is something which I think ICAM should be doing, producing forums, whether it's an electronic forum or a physical forum, getting together people to help them realize they are not alone. And when they are not alone, they can solve problems which the sum is greater than the sum of the sum of its parts. Okay? And that's something which we have seen time and time again. The individual person looking at these problems for the first time say, these are very, very hard. How do I solve it? And they give up. Whereas if they see other people do these problems successfully, they may think, oh, actually, I'm just as good as X. And why can't I do it? They have the tenacity there to then go about solving their problems. Okay, and this is we find particularly encouraging. Okay, so how I would like to put this is sort of appreciation in physics with mathematics put back in. So there's great enthusiasm and appreciation of science. Okay, and that is very, very much evident by website searches, by the programming on television. There is a great appetite for scientific programming, popular science programming. But if we want to encourage, and this is what we wanted to do as part of what I wanted to do, this Senior Physics Challenge, is to actually produce the next generation of scientists with an awareness that when they apply, there is a good chance that they will finish their degree, as opposed to 60% dropping out. Okay, they need to realize that in addition to just physics appreciation, they need to have real hard skills. So this is sort of physics with mathematics put back in. And those who are interested, here are our websites. There's the Senior Physics Challenge website there, and our general outreach, which details the things that I haven't had time to go into. Okay, thank you for your attention.
Questions for Anson? One thought, by the way, that, from the discussion last night and what you just said about the students sort of realizing that they have like-minded souls sitting in the room with them, that when Yuval was mentioning last night, and it came up from Elisa also, that when he came to Davis, he had an interest in perhaps trying to pursue some fundamental research on energy. And if we could convene out of our evidently developing interest in energy a summer school where we did exactly what you're talking about for graduate students who maybe haven't found quite the right niche for the fundamental research on energy but are interested, that could play a very, very nice role along the lines of what you're talking about. Other comments or thoughts for Anson? Jim?
I think that your comments just at the end about the discovering that other people share my interests, and I think as part of that having a group solving problem highlight a current tension within physics and perhaps other sciences too, but certainly physics, between the view of the lonely, brilliant researcher struggling with difficult problems by him or herself, as contrasted with the group problem solving, which I think is quite different from the traditional history of physics as it is held up to us frequently. And of course, it's not that either one or the other is somehow the right approach, but that both are
essential
important to be able to do.
But different people work differently, and group solvers solve problems in one way, and solvers do it in a different way, and we need avenues for both models of working to produce results.
Yeah.
Just on that line, I think it's really interesting, because if you look at what is the public perception of what a physicist does, if the perception is that the physicist spends their life isolated, working alone, you're going to attract a very different group of people than the people who have personalities where it's like, I don't want to be alone, I need to work with other people. And sort of setting up systems that allow both of those types of people to be successful and to have a public perception that both of those types of people are accepted and can be successful might be important.
The way in which this plays in a practical sense when you teach a course is that we often encourage students to work together solving problems and solving homework, for example, and that's very satisfying to them frequently. But then the potential downside is that you can become dependent on the group, and finally when you're sitting there taking the exam in the course, there you are all by yourself. And so this is the kind of educational tension I find in the ways in which we try to teach courses and involve students and make them feel comfortable with the material.
Any other questions or comments?
Just a small comment. This is an English is we also, I'm sure you know that not just on the senior level, we also have a science festival every year, and it lasts around a week. Engineering department is more important.
No, well, actually,
but I'm sure you guys
yeah. So yes. What I haven't listed is there's a whole list of other things we do, but what we also do is we hold typically a sort of 9 to 10 day long science festival as part of the whole university. So different departments, the physics department, chemistry department, engineering department, we all contribute and we all put in our pennies worth for what one exciting research is being done, and that ranges for ages from about 5 all the way up to adults. But that was far too broad for me to talk about in any great depth.
Okay, well, thank you, Anson. Really appreciate it. Now we should recover Yvonne's talk about the emergent labs. Let's see.
Can I just pick up on the last tape?